Hello there folks, today we're going to be talking about Heisenberg's uncertainty principle. But first we have to dive into some background knowledge. Quantum mechanics is a branch of physics dealing with the interactions and processes between atoms, photons, and other really small objects, as in 62 picometers small and smaller in diameter. A crucial and integral aspect of quantum mechanics is your understanding of Heisenberg's uncertainty principle. No, not Heisenberg from Breaking Bad, Werner von Heisenberg, a German physicist who quantified this uncertainty principle. What exactly is the uncertainty principle, you may be asking? In equation form, we represent this principle as delta x times delta p is greater than or equal to h, also known as Planck's constant, over 4 pi. Now I know, in your head you're probably saying, huh? What does this all mean? Not to worry, it'll all make sense very soon. In the universe, we have these specks of matter called particles. And in theory and definition, these particles inhabit a single specific, well-defined location at a single specific, well-defined point in time. With particles, we're able to ascertain their position at a well-defined, specified point in time. In addition to particles, we have waves. Waves are drastically different from particles. Waves are merely oscillations that transfer energy through space and mass. Think sound waves, or skipping a pebble in a lake near your house and ripples emitting from it. These are waves. Waves have this fascinating property called wavelength. The wavelength of light we see from the sun, also known as visible light, is between 400 and 700 nanometers. In essence, we can't see it. The wavelength is merely the distance from one peak or crest of the ripple to its adjoining or adjacent peak or crest. Its wavelength is merely a proportion, a direct proportion, to its momentum, which is its mass times velocity. With waves, you're able to ascertain its momentum, but unfortunately you cannot determine its position. Here's where things might get a little bit tricky. Every elementary particle or quantum object exhibits both properties of waves and particles. Now, wait a second. Didn't I just say that particles have a well-defined position which can be determined, but not a determined momentum? And wavelengths have a observable momentum, but not an observable position? Rather contradicting. How can a quantum object have both properties of a particle, which can be directly contrasted with properties of a wave? This is where we get the uncertainty principle. So how exactly does a quantum object become both particle and wave, or exhibit a wave-particle duality, as it's referred to by the physics community? Well, say you have multiple waves, and you stack each wave on top of each other. Suddenly the ripple, or the area in which all these waves overlap, begin to condense, to the point where it forms a ripple package, which is condensed and contained in one small region. Does that sound familiar or similar to any quantum object we may have discussed in the last few minutes? Yes, you guessed it. Now these waves are exhibiting particle characteristics. This is where we obtain the wave-particle duality, in which quantum objects exhibit both wave and particle properties. Although when we have a quantum object which exhibits both wave and particle characteristics, we lose a certain degree of uncertainty in both areas. We lose certainty in its position, which is a characteristic of the particle, and we lose certainty in its momentum, which is a characteristic of the wave. This doesn't just happen out of nowhere. When you have a quantum object which exhibits properties of both particles and waves, there has to be a certain degree of mutual cancellation and compensation due to these two objects having vastly different characteristics. When the certainty of this particle's position increases, the certainty of this particle's momentum decreases. Or in essence, we see this quantum object become more particle-like and exhibit more particle characteristics. And when you exhibit more particle characteristics, the certainty of position increases, yet there is no certainty in momentum, although there is some retention of its wave-like properties. Therefore, there is certainty concerning its momentum, although we can't be 100% certain of the momentum of this wave. Therefore, we use mathematical function to determine the probability or range of momentum this wave exhibits. Simultaneously, this package is composed of multiple waves. Therefore, the position can't be ascertained with 100% certainty. And as it gains more wave-like properties, the certainty of the position decreases drastically, Although, as I said before, we can use a mathematical function to gain somewhat of an idea of the range in which the position lies in. Due to there being multiple waves in this wave package, its momentum is uncertain. And due to the fact that you can never know the position of a wave at any point in time, due to it being, well, a wave, not a particle, there's a big uncertainty concerning its position. Now, to put this in equation form, the uncertainty of its position is delta x, and the uncertainty of its momentum is delta p. So, the uncertainty of its position times its uncertainty of momentum must be greater than or equal to Planck's constant, an exponentially small number, which we will not quite dive into in this video. Now let me provide you with a real-world example of the uncertainty principle. Say you're a physicist working at the Large Hadron Collider, and you want to observe a particle and how it interacts at the quantum level. If you want to grasp an understanding of this particle, you're going to have to use some light to observe it. And unfortunate for the purposes of the experiment, light emits photons. And the photons will eventually, at some point, knock the particle we're observing off its course. Now this particle we're observing has an unknown position and momentum. Now we can use some mathematical functions to gauge the probability of this particle being within a certain range with regards to these complementary variables, position and momentum. Yet, due to this collision, there is now a certain degree of uncertainty. And now I leave you with a quote from the wonderful Heisenberg of Breaking Bad. No, wait, Heisenberg as in Werner Heisenberg, not Heisenberg from Breaking Bad. Here's the quote. What we observe is not nature itself, but nature exposed to our method of questioning. And that, folks, is Heisenberg's uncertainty principle. Once a complex scientific topic, now an understandable scientific phenomena.